So in our previous lesson, we talked about one type of electrochemical cell known as an electrolytic cell. Recall that in an electrolytic cell, you have a non-spontaneous redox reaction that must be forced to occur through, or by rather, an external power supply such as a battery. The other type of electrochemical cell is known as a galvanic cell or voltaic cell, two different names for the same thing. In this type of electrochemical cell, it's kind of the opposite. You have a spontaneous redox reaction, first of all, that occurs, and this reaction produces electricity. So electrons are forced to travel through an external circuit, and these electrons then, basically the movement of these electrons is electricity. And so an example of a galvanic cell is a battery. Inside a battery, this could be a car battery or a little battery inside one of your electronic devices. You have a spontaneous redox reaction that occurs. This reaction produces electricity, which we can then use to power our electronic devices. So let's take a look at a diagram of a galvanic cell. So go ahead and pause the video, draw this diagram, and label all the parts of this galvanic cell. Go ahead and pause now. So here's the basic design. We have two beakers, and we have two different solutions in these beakers. And then in each of those solutions is some metal. So in the left beaker, we have a piece of copper metal. And the copper metal is in a solution of one of its own ions. That's important to note there, is that we have some metal in a solution of one of its own ions. This time we have a solution of copper 2 sulfate. What's important also to understand is that this solution has copper 2 ions in it, a whole bunch. Also has sulfate ions, which are spectator ions, so we don't really care about these sulfate ions. In the beaker on the right, we have a solution of silver nitrate. In that solution of silver nitrate is silver metal, so that is the other metal. This solution contains silver ions, of course, along with nitrate ions, but the nitrate ions are a spectator, so we don't really care about those. All we care about are the silver ions. The two beakers are connected to each other through number 5, which is called a salt bridge. The salt bridge contains one of two things, either a paste containing some solution of an ionic compound, or just simply a solution of an ionic compound. So this could be, and is often, a solution of potassium nitrate. The reason why we often use potassium nitrate in the salt bridge is because neither the potassium ions nor nitrate ions will form any precipitates when they ultimately go into one of those two solutions. Those metals that I referred to earlier, the copper and the silver, are connected with wires. So these squiggly things here are wires, and they're attached to some sort of measuring device. That measuring device could be a voltmeter. A voltmeter measures voltage, which is one property of electricity, or it could be an ammeter. An ammeter measures currents, which we talked about in the previous lesson. So this is the basic design of a galvanic cell. We got two beakers with different metals in them, different solutions, and those two beakers are attached to each other with this U-shaped glass tube. So that's a glass tube filled with some sort of solution. Here I put kind of cotton balls in the ends to prevent all the solution from dumping out. And so that is what a typical galvanic cell looks like. There's a diagram in your book as well on page 801. It's a different one. This one shows zinc and copper, but the same idea as is what's shown here. So let's say that you put all this together, put the salt bridge in, and lets the reaction occur. So what actually happens during this reaction? First of all, electrical current flows from the copper metal to the silver metal. So it's important to know where the electrons are flowing, how they're flowing through the external circuit, these wires that are attached to the voltmeter. So in this particular case, I have given you the direction that the electrons travel through the wires. In the future, I will teach you how to determine this on your own. So electrical currents essentially is electricity. Electricity essentially is the movement of electrons. So let's show in our diagram the path that the electrons take through this external circuit. So we said that electrons flow from the copper. So I'm going to put electrons on both sides here. From the copper towards the silver metal. So we have a transfer of electrons occurring, so something is losing electrons clearly, and something else is gaining electrons. So that tells us that a chemical reaction is occurring. Not just any chemical reaction, but a redox reaction. Something is being oxidized, and something else is being reduced. Now, here are some observations of what happens. So let's say we let the reaction go for a certain period of time. You take the galvanic cell apart, you determine the masses of the metals, and this is what you get. So first observation is the mass of the copper metal, which is known as an electrode. So let's label that here. So this is one of the electrodes. Again, electrode meaning the surfaces where the redox reaction occurs. In a galvanic cell, the electrodes are the things attached with wires to the voltmeter. So the mass of the copper electrode decreases by 1.00 grams. And the mass of the silver electrode, so let's label that in our diagram. This is our other electrode. So we have two electrodes, one on each side. The mass of the silver electrode increases by 3.40 grams. And lastly, that solution on the left, which contains copper 2 ions, remember that copper 2 in solution is blue, and that solution over time, as the reaction occurs, becomes darker blue. So what does all this mean? What can we make of these observations? What does the decrease in the mass of copper and the increase in the mass of silver have to do with this reaction? So let's start here. Let's take the mass change of each electrode and convert that to moles. So convert the 1 gram of copper to moles and convert the 3.40 grams of silver to moles. Go ahead and pause the video while you do those calculations. All right, so here's what we get. We get a decrease in copper of 0.0157 moles, and we have an increase in the moles of silver, 0.0315. Notice anything about those values? Talk more about those in just a minute. All right, next up, let's write equations for what is occurring in each beaker. Each beaker, by the way, is known as a half cell. So the whole thing is called a galvanic cell, and then half of that is called a half cell. Coincidentally, the process that occurs in each half cell is known as a half reaction. So again, we have oxidation half reactions, we have reduction half reactions. So let's start with the half reaction that occurs at the cathode. Now, what process occurs at the cathode? Is that oxidation or reduction? This is where our word association comes into play. Cathode starts with a consonant. The process that occurs at the cathode is reduction. Remember, both cathode and reduction start with a consonant. So that's one way to help you remember. Well, let's take a look in at our galvanic cell and see where reduction occurs. So in which half cell, the copper half cell or the silver half cell, is something being reduced? Well, remember, the electrons go towards the substance being reduced. So there we go again with the consonants. So something over here on the right side, this half cell where we have silver, something is being reduced. Now we have two substances here that potentially could be reduced. So let's take a look at a couple different possible half reactions. Don't write this down just yet, because only one of these is the actual half reaction. So we have two choices. Either the silver metal itself is being reduced, or the silver ions in solution are being reduced. Those are the only two substances in the silver half cell that are involved in the reaction, the silver metal and the silver ions. So remember, in a reduction half reaction, the electrons that are being gained go on the left side. So if the silver metal is what is being reduced, what would you make? Well, remember, when a substance is reduced, its oxidation state decreases. So you would make Ag minus. If the silver ions are what is being reduced, then what would you make? You would make silver metal. So the question is there a possible oxidation state of silver of -1? I don't think so. So this is not what happens. What does happen is that the silver ions are what is reduced. So go ahead and write that in the space. All right, how about in the anode half reaction? So what process occurs at the anode? Well, the word anode starts with a vowel. So the anode is where oxidation occurs. So again, let's take a look at our galvanic cell. Which half cell represents the where the oxidation process occurs? Well, remember the electrons go away from what's being oxidized. So now we got vowel association. Anode is where oxidation occurs. Electrons go away from what is being oxidized. So over here on the left half cell, something is being oxidized. Again, we have two choices. So let's take a look at equations for both of those. Either the copper 2 ions are being oxidized, and don't worry about why it's 2 electrons, I'll show you why later, or the copper metal is being oxidized. Remember, when a substance is oxidized, its oxidation state increases. So if the copper 2 ions are oxidized by losing 2 electrons, what would you make? You would make Cu plus 4. And if the copper metal is oxidized by losing 2 electrons, what would you make? So which is a more likely oxidation state for copper? Plus 4 or plus 2? Well, copper does not form any ions with a plus 4 charge, so that one is out. Don't write that one down. Go ahead and write the other half reaction in the space provided. All right, now that we have our oxidation and reduction half reactions, we can combine them to write the overall redox equation. Now, something to be careful of, we have a different number of moles of electrons gained than lost, and it looks like I just wrote that second half reaction wrong. Let me fix that, sorry about that. There can't have both substances being reduced, so we have one mole of electrons gained, 2 moles of electrons lost. That can't be so we need to make number of electrons gained and lost the same. I don't recommend that you do it like this. I recommend that you change each coefficient, but nevertheless, I'm going to write it this way this time. So here's what we end up with. We have 2Ag plus Cu makes 2Ag plus Cu plus 2. And those electrons will cancel each other out. What do you notice about the amount of copper that reacts compared to the amount of silver that is produced? I'm talking about copper metal and silver metal. Well, it looks like for every 1 mole of copper that reacts, you make 2 moles of silver. I think we already knew that, didn't we? Based on our calculations here. That's what we see based on the calculations, and we can see that corresponds with our balanced redox equation. We have a 2-to-1 ratio of silver to copper. So again, let's also think about the observations that were recorded earlier. It was noted that the mass of the copper electrode decreased. Well, notice what copper is in this reaction. Copper is a reactant, so of course the amount of copper will decrease. Likewise, we observed that the mass of the silver electrode increased by 3.40 grams. And again, it makes sense that silver is a product of this reaction, so you're going to make more silver. The other observation was the solution that contains copper 2 ions gets darker blue. Why is that? Well, that implies that the concentration of the copper 2 ions in solution increases, which again makes sense that copper 2 is a product of this reaction. So that explains the redox reaction. Well, what about the function of the salt bridge? So what actually is the purpose of the salt bridge? So it says here that positive and negative ions inside the salt bridge migrate through the salt bridge to bounce electrical charges in each solution. And this movement of ions from the salt bridge into the different solutions in your half cells prevents these solutions from developing an electrical charge. This process of polarization developing an electrical charge. So it keeps those solutions neutral. Without the salt bridge, those solutions would develop an electrical charge, and if that were to occur, the reaction would stop. So without the salt bridge, no reaction occurs. Need a salt bridge in order for that reaction to happen. So let's go back to our galvanic cell and show exactly which ion from the salt bridge goes into which solution. All right, so let's start with our copper half cell. So remember, in this half cell, we have copper metal being oxidized to copper 2, and those 2 electrons that are being lost are what goes through that external circuit through the voltmeter. So ignoring the effect of the salt bridge, what is happening to the charge of that solution? Go ahead and think about that. Pause if you need to. Well, you're taking copper metal and you're making copper ions out of it. That solution is becoming more positive. Well, to balance out that increase in positive charge, which ion from the salt bridge is going to move into this solution? The potassium ions or the nitrate ions? So in this case, the nitrate ions from the salt bridge will move into the solution where the copper 2 ions are in order to keep that solution neutral. Now, going back to this electrode has a name. Remember, there's 2 types of electrodes. We have cathode and anode. Which electrode is the copper? Well, it's the electrode where oxidation occurs. This is the anode. Interestingly, what is another name for a negative ion? Well, negative ions are called anions. So check that out. The anions from the salt bridge will migrate towards the anode. All right, let's take a look at the other side. On the other side, what's happening? We have silver ions that are being reduced to make silver metal. So we are losing positive ions from the solution. Those positive ions are turning into silver atoms. So how do we keep this solution neutral? This solution is becoming less positive, if you will, more negative, however you want to look at that. So which ion from the salt bridge needs to move into this solution to keep it neutral? Well, in this case, potassium ions. Well, what is another name for a positive ion? Those, of course, are called cations. Well, which electrode is this? This is the electrode where reduction occurs. The electrode where reduction occurs is known as the cathode. Which ion from the salt bridge goes into the solution where the cathode is? That, of course, would be cations. So cations migrate towards the cathode. So how about the charges of those electrodes here? We know that from previous lesson, in a galvanic cell, the cathode is the positive electrode and the anode is the negative electrode. Well, how are you going to remember that? Well, remember that the electrons spontaneously flow through the wires in a galvanic cell. We have a spontaneous redox reaction that occurs. Electrons are negatively charged, so what are they attracted to? Well, they're attracted to anything that's positive. So that might help you to remember that the electrons move towards the positive electrode in a galvanic cell. Conversely, like charges repel each other, the electrons are going to go away from the negative electrode, in this case, which is the anode. In an electrolytic cell, it's opposite because you're using an external source of electricity to force the electrons through the wires and to the different electrodes. So the anode is the positive electrode and the cathode is the negative electrode. Still, oxidation occurs at the anode and reduction occurs at the cathode, but the sign conventions for those electrodes are different. On page 804, we can see a diagram of this galvanic cell. We have a copper in the left half cell, silver in the right half cell, and we can see what's happening. with the copper atoms and the silver atoms. So we're taking copper, turning that into copper 2 ions, and we're taking on the other side silver ions and turning them into silver metal. So the copper electrode would actually starts deteriorating and starts disappearing as that substance is being used up. And what we would see is that the silver electrode, we get a buildup of solid material on that particular electrode. So letter C, this will be important for later on. A cell in which all the solutions are 1 molar, and if there's any gases present, the pressure is 1 atmosphere. This is known as a standard cell. Later on, we'll be talking about standard electrode potentials or standard cell potential. And so just know that usually we're talking about galvanic cells where the electrodes are placed in solutions that have a concentration of 1 molar. All right, next up we have shorthand notation for galvanic cells. And so for the galvanic cell that we just diagrammed, the shorthand notation would look like this. So this one line here between Ag and Ag plus and between Cu and Cu plus 2 represents the electrode interface. So you have a piece of silver metal in a solution of silver ions. And in the other half cell, you have a piece of copper metal in a solution of copper 2 ions. So that's how we interpret the single lines. The double line here, that represents our salt bridge. So the two solutions are attached to each other via this salt bridge. Now, it's also general convention to put whatever's being oxidized on the left side. So in this case, we have the silver metals being oxidized, and whatever's being reduced on the right side. In this case, we have copper 2 that is being reduced. But don't assume that is correctly drawn. But this is by convention. So technically, we have these wires here. The electrons are going in this direction through the wires. All right, that concludes this lesson. Next time we'll be talking about standard electrode potentials. We'll be calculating the voltage associated with some electrochemical cell, the voltage produced by a spontaneous redox reaction in a galvanic cell, or the voltage required to make a non-spontaneous redox reaction occur in an electrolytic cell. All right, thanks for watching.